Hi everyone. Today I'm going to discuss a paper which is related to our current project, and which it is also a very interesting paper, and the resources guide program synthesis. The authors are the Tristan Noss, D. Wang, and Nadia Policarpos, and Jan Hoffman. And so first of all, the program synthesis is a task where the input is a specification and the output is a executable program. And an example here is that the user may want to say, I want to find the intersection of two sorted lists, and the synthesizer will find the user the program they want, the intersection function. Approach of the such synthesis is called type-directed synthesis, where the specification is described by refinement type. Here you can see the user want to find a function common, and the input are two lists. The XS is the sorted list, and another list is YS is also a sorted list. And the output V, the user expect that the output should also be a list, but in addition, the element of the output should be the intersection of the element of X and the element of YS. And the synthesizer will find the user such programs. I will discuss this program later. Yeah, this one. You can see what these programs do is it first scan the elements in the first list XS, and for every element X in the list, what this function do is it try to decide whether X is also a member of YS. If it is, we include X in the result. Otherwise, we go to next element. And another possible implementation is we scan X as the first list and the Y as the second list at the same time. Every time we take an element from the left and an element from the right, and we compare them. If X is less than Y, we go one step on the second list. If X is less than Y, we go. Yeah, if X is less than Y, we discard X and continue. If Y is less than X, we discard Y and continue. Otherwise, X is an element in the result. And you can observe that the complexity of the first implementation is big O m plus n, and the complexity of the second implementation is big O m plus n. So in some case, the user doesn't want just a correct solution. She may want a correct but also efficient solutions, just like the second implementation. And the left-hand side is what we have. We have the state-of-the-art synthesizer, which can find us correct solutions. And what we want here is a synthesizer which can find us an efficient solution. We can say we want to find the intersection of two sorted lists in linear time. And the author's build is named ReSyn. And this is the first resources-aware synthesizer for recursive programs. In this talk, I will introduce the three components of ReSyn. The first one is how can we specify the problems in ReSyn. How can we say we want to find solutions who can return the results in linear times. And the synthesizer contains two components. The first one is how can we analyze the complexity of a given programs, and how can we search for a program which satisfies the resources bound. So let's first talk about the specifications. First, how can we describe the correctness specification? We talked this in the first example, we can use the refinement types. And for the resources bound, we can use the resources annotations. And the refinement type synthesis is these two, the refinement type synthesis and the resource annotations are both the previous works. And in this paper, the author combined these two previous works to get a type direct program synthesis with resources annotations. And here, this is a refinement type, where B is the base type, and beside here is a refinement. So we use the refinement in blue color to describe what we want by the intersection of two sorted lists. Here is an example refinement. The elements of the width of the output should be the intersection of the elements of the input. And here is another example of the refinement. You can see this refinement type says that the output should be a nature number. And yeah, and the synthesis with refinement type is the goal of the synthesis with refinement type is to find the implementation of the whole here, the question mark here, such that the implementation satisfy the given type with refinement. Yeah, and this tool is called Sync-it.
Hi.
Hi.
Yeah, I have a question. So, what kind of logic can we put in the refinement type? I mean the
well,
yeah,
what kind of
the file here?
In Sync-it, the author check the constraint on refinement type by the SMT solver. So I suppose any logic supported by SMT solver can be used to describe the refinement. And yeah, and so the author built a Sync-it, the synthesizer with refinement type. And the two inputs of Sync-it is the functional specification, and also the Sync-it will take a library function as input, where the output can use the output implementation can contain library functions. And here you can see there is a one library function member here. And yeah, and now how can we specify the resources bounds in refinement type? The idea is that we add a potential to the refinement type. The potential phi here. Let's see an example. This is still finding the intersection of two given sorted lists. Now, instead of finding an arbitrary solutions, the user may say, I assigned one potential to the xs and one potential to the list ys, which means that we have these notations represent the resource we can use in the implementations. And here one means that we have one potential for each element in the list, and one here means that we have one potential for each element in the ys. So the total potential we have is 1 times the size of xs plus 1 times the size of ys. Okay. And yeah, we also have the library function here, but we should know that the library function should also be annotated by the potential. Here, the member function is not just finding a member. It's not just decide if a given element is a member of a list. You also consume one potential here. You can see, yeah, it take one potential, and the output contains 0 potential here. We ignore we omit the 0 here, which means that we consume one potential when we consume the one potential for each element in the ZS when we run the member function. So here is the problem of the program synthesis with resources bounds. we have one additional specification which described in the resource bound we want to satisfy. Here, if we say that we want to find a linear time solution, it will give us this. Now, how can we analyze the resources usage of a given program? Let's look at this example implementation. Yeah, what this function do is, okay, I'll describe the function again. You take two sorted lists, xs and ys, and you match the xs. You take one element x from the list xs and check if x is the member of the second list ys. If it is the element of the it is an element of the second list, we go to the else branch. So we include x in the output list. Otherwise, we discard x. And now we know that each time we call member function, we will consume one potential for each element in the list. How can we reason about the overall resources usage? Okay, let's recall that this is the type signature of the common function. The input we have the input we have the total potential we have is the size of xs plus size of ys. Okay, so how can we partition let's focus on the size of ys for now. How can we partition the all resource potential we have between function calls? You can see there are two function calls. Actually, there are three, but the then branch and the else branch cannot happen at the same time. So there can be at most two function call in one run. For the first call, we say it will consume potential P. And for the second call, we assume that it will consume potential Q. For the member function, since it consumes one potential for each element in the list, so we know that P should be at least one. For the similar reasons, since the common function, the signature of the common says that we will consume one potential for each element in the list ys, here ys, so Q should also be at least one. So if we want to share the input potential, at least A1, the potential of the ys here, we need to find a way to share the 1 here, which means that 1 equal to P plus Q. And we also have the constraint that P is at least 1 and Q is at least 1. Yeah, when we check this curve in the SMT solver there, yeah, we will know that it's invalid. There is no solution. And this how we can know the resource usage for a given programs, but how can we search for them? A naive approach is that we can do the enumerate and check, which means that we can have a synthesizer which enumerate all solutions satisfy the type without the resources annotations, and then we check if the complexity, the resource usage of the candidate solution satisfy the bound. If it is, then it is a solution. Otherwise, we go back to the synthesizer. Another possible approach is using a local resource analysis, and which called ResourceGuide Synthesis, which we analyze for the resource usage when we search for the chain, and we can reject impossible programs early. Okay, still in these programs, assume that we are searching for the implementation of common, and you can see this is a partial implementation. There is still a hole here, but we don't need to find the implementation of this whole. Why? We can analyze the resource usage for these partial programs, and we can find that for this partial program, the bound cannot be satisfied. So we don't need to fill this hole, and we don't need to search for more program. And we can reject this template early. And we can try another template where you can see we put a hole here, which means that we go backtrack and try another possibility. Okay, in the evaluation, the authors want to answer the question. The first question they also want to answer is that can the tool generate faster programs than the tool without the resources bound? And the second question they want to answer is their tool efficient enough to find solutions? And the last question is if the local resources analysis is efficient at guiding the search, if the local resource analysis is better than the enumerate and check process. They have 65 benchmark at all, where they can solve 54 of them, and they can improve 2 of them compared to the solver without the resources usage bound. And they can find more. They can find solution with they can find solution with better performance. Here is an examples. If we don't have the resources usage bound, the solver will give us the 2 to the n solution for the compressed benchmark. Yeah, they call it compress x4 twice. So it's Tn equal to 2Tn. And if they give the bound that they want to find a linear time solution, they will get a solution whose complexity is big O n. Here is another example. Insert into a sorted list.
So Qinheping, can you go back? This is Tom. Can you go back one slide? So if the model were that there was function caching going on at runtime, the program on the left would also be order n, wouldn't it?
Sorry,
because the compressed x4 would be found in the cache.
Yes. Yes.
So it's not as bad a program as one might think, the 2 to the n.
Yeah, and yeah, I agree. And we can easily use in a new variable to store the compressed.
Yeah. Okay. Thanks.
Yes. So I'm not sure if we can say a real improvement. But yeah, but okay, let's move to next examples. In this example, they want to do the insert to the sorted list, and the implementation in the left-hand side, what they do is they check. Let me see if the list is empty, then you append the new element to an empty list. Otherwise, you check if x is less than the smallest numbers in the list, the sorted list. If it is, then we can just oh, I see. You can see here the insert ys is not required actually, because we know that the list is sorted. So if x is less than y, x must be the smallest element in the new sorted list. So we can just append x at the beginning of the sorted list. And you can see, although in the worst case, both the complexity of both implementations are both big O n, but actually we can say the complexity of the second implementation is the big sorry, how can we write this? Oh, pen is the, oh, how can I write on the, oh yeah, sorry. It should be the big O. They call the greater the number of the y greater than x. Or y less than s. Sorry. Okay. If we have another quantity says that which is the number of elements in the list such that y is less than x, the actual complexity of this implementation is big O, the number of elements less than x in the list. They call such complexity the dependent bound, where the bound is dependent on the input. Okay.
They also could use big theta notation, which means that it's always going to take that much time and is upper bounded by it. So like the program on the left is big theta of n. And I guess the program on the right is big theta of sharp y less than x.
I'm not sure. Big theta. Sorry, so Tom, can you say it again? I'm not sure.
So there's another symbol that people use to describe out. I mean, there are some other. There's big O, there's little o, and then there's a capital omega, and then there's big theta.
Yes.
And big theta, if I remember correctly, means that not only is it big O of n, but it also will always take order n time. So the program on the left is big theta of n.
I see.
The program on the right is big theta of sharp y less than x. That would be a sharper way of describing it.
Yeah. I see. Yeah, we can describe the lower bound. The lower bound of the left hand side is greater than the right hand side. Yeah. Okay. Yeah, the one recursive call per element in the list that is smaller than x. Okay, and they have some compare the time, but the result shows that with the resources bound, they solve the problems lower, but they have their complexity bound guarantee. And yeah, they have some benchmark on which they can find solutions satisfy the dependent bound. Here is they find fastest implementation on 1, 2, 3, 4, 5, 6, 7, and they dependent on 1, 2, 3. Also, okay. And they also compare their tools to the enumerate and check the naive approach, and they find that the results turns out that they can solve more problems than the naive approach. Okay, this is the ResourceGuide Synthesis, and the overall idea is that they have the annotations on the type, and when they try to search for they have annotations on the type refinement type, and when they search for a term, they just need to try all possible share of their annotation, their potential, and and check the term satisfy the refinement type. Okay, any question about this paper?
So, so these kinds of annotations are the same kinds of things that Jan Hoffman has used for analysis, resource analysis of resources of programs, and his system is able to do amortized complexity.
Yes, yeah.
So, are there programs does this also open up the ability to characterize the behavior in an amortized sense as well?
I think this annotation is already amortized, right? They have one potential for each element. Isn't it the idea of the amortized annotations?
Well, I'm saying that's the idea that they use, but does it automatically get you a program that, I mean, do they have examples where they say the cost of this program is such and such in an amortized sense? Or is it the fact that they've used this notation, they just get that for free?
Let me check. I'm not sure.
Maybe Tom, do you have in mind an example?
Well, let's see. I mean, the simplest example, I think, is the cost of the stack manipulations in a depth first search. That you are, in the worst case, you can be, or when you're finding strongly connected components, in the worst case, you can be popping off order n because there could be just one gigantic component. But over the cost of the whole algorithm, the stack manipulations, I mean, you will do n such operations, but the total collection of operations, the total cost of all the operations you do is order n, even though, so you can't just say, I'm doing n operations, the worst case cost of one operation is order n, and therefore it's order n squared. That's true, but in an amortized sense, the total cost is order n. It seems like you would get this for free because you would just say,
I think you do get it for free.
That element just has one thing.
Yeah, I think the example with trees are the same, and they do those trees. So I think it is the same.
Okay.
Like when you traverse a tree, right? It's kind of the size of the total tree doesn't change.
Yeah.
But you can't. You need to reason about the fact that you're keeping the cumulative cost of traversing the whole tree. So I think that's, yeah, you're right that you get it for free.
Yeah. Okay. Thanks.
Okay, if we have no further question, this is what I want to discuss for today, and maybe we can discuss any other topics or have some social activities for the rest of the seminar.
Maybe can you tell people a little more about the type system?
The refinement type system.
Yeah, for this particular potential stuff. So I think one thing you can do is just maybe open the paper and comment a little bit on how things are created.
Okay, I think it's a great idea. Yeah, the first thing I found it interesting is that to understand how the annotation works is first is this example where they want to implement the triple function. You can see that what the triple function do is they take one list and they return they append this list by itself twice. So so all we know is that the length of the output should be 3 times the length of the input. And we have two possible implementation. One is the append. We first append the we first append, you can see it's almost the same implementation. They are almost the same, but you can see the difference that this application appears as the second argument, and here it appears as the first argument. But this difference leads to the difference on the resource usage. Since in our implementation of append, we assume that we only consume one potential from the first list argument. So you can see here, this append will consume one potential for each element in the list L, and this append will consume another one potential for each element in the list L. So it's at all is 2 times the size of L. But in this implementation, you can see it's different, because for this append, it also contains you also consume one, but since the length of this value, the append LL should be the twice of the length of L. So the resources usage of this append should be 2 times the size of L. So at all, it is 3 times the size of L. And yeah, this is a good, I say a good example to understand what they do for you with the annotations. And they have the type system. Their type systems. This is the language of the solutions. They can have true, false, empty. This should be the empty list, and the const and the lambda fix, the abstract, and they also have if then else, the match. This is the match, and application, let, tick. Tick means that each time we call tick, we will consume the constant resources C. Okay, true, false, no, constant, lambda, nothing special. And this is their type system. They have a refinement type where they have a base type, which can be a Boolean. Sorry, which can be a Boolean and or a list of T or M times A here. And they have the resources annotations, the phi here, where phi can be phi is also a refinement. Precise refinement, phi is also a refinement, but different is that the resource refinement, the resource annotation is a number, while the type refinement is a Boolean value. Okay, let's look at some rule of it. I will take some example rule to explain how their type tracking system works. First is the first one I want to talk about is this one. If you look at here, they says that if the tick C is valid, the tick C is can be checked only if we have we have the C potential in our context. And T conceal positive and negative, yeah. And when the C is a negative number, then we don't need to have the C in the, we can add another C potential to our context. And here is how we share the potential. These symbols is the share symbol where if we have a context gamma contains some potential, we can share the potentials in gamma to gamma 1 and gamma 2, such that the gamma 1 can consume potential yeah, what we have, and the gamma 2 can consume the rest of the potential in gamma. And yeah, here is how we share the potential. If the Boolean, we can, if it is the length of the, yeah, here, and if it is the shear potential to satisfy the sum should be the original potential. Okay, and this is the type check-ins, and then this how they synthesize the solution given a resources found. What they do is they do the bidirection type check-in, where given a whole, we can first try to do the top-down search. For example, we given a whole, we can guess given a whole satisfy this type, we can guess that this whole should be implemented as a latent. After this guess, we have some sub goals. We want to fill this hole and this hole with the sub goal, and we can then try to implement this these two holes with the sub goals, and we have two new sub problems, and we keep doing so until we cannot generate we cannot check the type. So we do the button up type generation. Button up type generation, yes. We try to enumerate some terms satisfy the given type. And yes, and that's it. And that's this they introduce how to solve the constraint after they build after they have the type check-in. They enumerate some term how to check if the enumerated term satisfy the type given type. Yeah, that's basically what this paper talk about. Any question? Oh. Okay.